Okay, this section of notes is regarding motion in general, and then also speed and velocity. So let's first begin by taking a look at what we believe to be motion. We discussed a little bit yesterday about what we thought motion was all about. And we know from the Greek times that Aristotle believed that every object had a place, and that when an object wasn't in its special place that it liked to be, that it would strive to return back to that place. And Aristotle believed that the distance that an object had from its original place determined its motion. Galileo, who was the father of modern science, as opposed to Aristotle, he added to this idea of time being involved. So he had a concept about motion being around a distance, and also there was a time component as well. And he was one of the first people to come up with this idea of rate, of how fast something is happening by taking the distance divided by the time. So today, our modern concept of motion, we already talked about, is that we can describe motion using words by describing motion around a frame of reference. But as we saw in our opening activity, that an easier way for us to describe motion is mathematically, so that you can describe the speed of something, the velocity of something, the acceleration of something. So our modern idea of describing motion using mathematics, one of the ways that we do describe motion is that we describe the speed of something. It's a measure of how fast or how slow something is moving. And you can mathematically find the speed by taking the distance that the object moved divided by the time. And we abbreviate this as S equals D divided by T. So what do we mean by time? Time is a length of time that passes from one event to another. And I know you're not really supposed to use the word to define the word, but there's no other way to do that here. And then time can be measured in seconds, minutes, hours, any other SI unit that is appropriate, usually seconds. Distance, the other component of the speed equation, is defined as the length of the path between 2 points. And it is also represented in SI units, meters, kilometers, centimeters in our class. Also feet and inches, but we tend to use the SI units in the science classroom. Now there's different kinds of speed. The first kind of speed is instantaneous speed, the speed something has at that particular instant. When you're driving in a car, the speedometer is reading your instantaneous speed. When you pass by the state policeman and he hits you with the radar gun, he cares about your instantaneous speed, the speed you're going at that instant. If he pulls you over for going 85 in a 35 zone, you can't say to him, well, gee, officer, just 2 minutes ago I was going 35. He doesn't care. He cares about your instantaneous speed when he clocked you going 85. And then we have something called an average speed. The average speed is the total distance divided by the total time that you travel. So if when I went to college in Philadelphia, my mother used to always ask me, like, well, how was your trip, and what speed were you going? And I would always give her an average speed, Oh, I went 65 miles per hour on the turnpike to get from Philadelphia back home to Pittsburgh. And she would seem content with that. But little did she know that, at times my instantaneous speed was well under average speed and well over. For example, when I pulled in to a rest stop and I stopped my car, I wasn't going 65 miles per hour. I was going rather slow, maybe 25 miles per hour in that parking lot. I stopped and was going 0 miles per hour. And then to make up for some of that, I would sometimes go a little faster than 65 miles per hour, maybe 85 miles per hour. But she asked me, what's your speed? She didn't clarify instantaneous or average, so I'd give her an average speed, 65 miles per hour. Speed is relative to something else, usually to the Earth's surface, and we talked about this in our introductory activity and introductory discussion. We can describe motion around a frame of reference. Speed, we use the frame of reference also. We assume that the Earth isn't moving, so that you go from one point to another in a certain amount of time. We're not taking into account that you might be going faster because you're going with the revolution of the Earth or against the revolution of the Earth, so to speak. So, what is the difference then between speed and velocity? Okay, so speed we said is how fast or how slow something is going. And in velocity, it's not just how fast something's going, but it also includes the direction that I'm going as well. Okay, so I can be moving at a constant speed. Okay, constant speed is if I put my cruise control on, I set it for 55, I'm going to go 55 miles per hour the whole time that the car is moving until I hit the brake, right? So if I'm going to say I'm at a constant speed, then I am not changing my speed. If I want to say I'm going at a constant velocity, then there's no change in distance, there's no change in speed and direction, okay? So moving at a constant speed is different from moving at a constant velocity. If I put my cruise control on and I'm going 55, but then I kind of go around a curve, and before I was going north and now I'm going west, I'm still moving at a constant speed at 55 miles per hour, but I'm not at a constant velocity. I've changed my direction. So let's take a look at some speeds and some objects in metric terms, because we're used to using miles per hour and we kind of have in our mind what that is. So a normal baby, you know, not a baby that's maybe taking steroids or anything like that, but a normal baby crawling goes about 1 kilometer per hour or 0.28 meters per second. A person on a bicycle, and we're not talking about a professional bike rider, just someone taking a leisure bike ride, would go about 80 kilometers per hour or 22.2 meters per second. So if you're bicycling in the savannah on the Serengeti, okay, you're going to have to go a little faster because a cheetah can run. It's not its top speed, but its average running speed is 100 kilometers per hour, or 27 meters per second. So, you know, if you are biking through the savannah, I don't recommend a leisurely bike tour because something can actually catch you quite easily. And then the fastest airplane, the Concorde SST, it can go 3,600 kilometers per hour, or about 1,000 meters per second. So what if we want to calculate speed? Get one of these nice algebra word problems in physics. A train is traveling from city A to city B. It takes 2 hours to arrive at city B. The distance between the two cities is 22 kilometers. How fast is the train traveling? So whenever we do problems like this in the classroom, I'm going to be giving you one of these grids. Now, you could be very good at math, and you feel like you don't need to fill in a grid with the variables and then list out the equation and substitute and solve the equation and give your answer in the appropriate significant figures. However, if you don't give me all of that, then I can't give you partial credit. I usually make problems like this worth 5 points, where you would get a point for having the right variables, the right equation, for substituting right, for solving correctly, a point for the correct answer, a point for the correct unit. Okay, so if you give me the wrong answer and everything's right except for your significant figure is off, because we know how easy that is to do, I will have no choice but to take the full points off if you don't give me any other work. So it's your choice. You don't have to show the work. If you think all your answers are going to be perfect and in the perfect significant figures, but that's not most of us. So let's see how we would fill one of these grids in. So here are my variables. I want to know the velocity, how fast is the train traveling? And you notice how we kind of use speed and velocity interchangeably? We do that a lot in these kinds of speed and velocity problems. So be careful, you know, you can use those two terms interchangeably unless it's specifically asking for velocity and a direction's given, then you have to give a direction in your answer. The distance, we said that the train traveled, 220 kilometers. The time was 2 hours. I can use the equation speed or velocity equals distance divided by time. I'll substitute in. This is what I have for the distance. I don't know the velocity. That's what I'm looking for. Here's my time, and I'm going to solve. And then I put my answer over here. Now, is this answer correct? No, it isn't, because I don't have this answer written in the appropriate significant figures. So if you were to give me all this, I might take off 1 point because you have the answer wrong. You have the correct unit, kilometers divided by hour. You substituted correctly, you had the right equation, you had the right variables, but you just forgot to put the sig fig in. This should be what? 2 sig figs divided by 1 sig fig should be 100. Now, in our course, we really only care about motion in one dimension, but in your next physics course that you take at the high school, you're going to want to know things maybe moving, not just the speed something's moving, but the direction that it's moving, so you at least need 2 dimensions. And when we are looking at motion in more than one dimension, we use these things called vectors. Vector quantities have a magnitude, a number value, and a direction involved with them. Magnitude means how much, direction, which direction. I can represent then something like velocity that has a magnitude and direction with a vector. So here I have a vector, looks like an arrow, and the length of the vector tells me the size. So here I have 50 kilometers per hour. This one's also 50 kilometers per hour, so notice these arrows are the same length. This velocity is double, 100 kilometers per hour, so it's double the length. Okay, these are both going in the same direction, east. Even though these two have the same magnitude, they're going in different directions, so the arrows are pointed in different direction. So the arrow length represents the magnitude or the speed, and the direction shows the direction. And then when I add, subtract, multiply, or divide, resultant vectors are the algebraic sum of the 2 vectors. Okay. We can also have motion that happens in one dimension, but it's happening in a circle. I'm moving in a curved path, so I'm constantly changing my direction. So if I were going at a constant speed as I'm going in a circle, like a NASCAR driver, I'm at 100 kilometers per hour, let's say, going around my NASCAR track here. I know my NASCAR track looks a little circular instead of oval. Is my velocity also constant? And the answer to that is no, because I can be moving at a constant speed, but not moving at a constant velocity, because when I move in a circle, I'm never moving at a constant velocity because my direction is always changing. Okay, we're going to when we reconvene, we are going to be taking a look at doing some of those math problems and practicing, pulling out our variables and substituting and figuring out our speeds and velocities.